So let me try if you can see my slide first. So can you see the slide?
Yeah, we can see the slide.
Okay, how about the forward? Okay.
Yeah, it is moving.
Okay. Okay, so thank you, Jerry, for your introduction, and I'm very happy, to be here again, to meet you guys. And last month I were in ACDRC grand opening ceremony, and I'm happy to meet many friends in Brno again here. Okay, so I'm going to get started on my presentation. Today's topic is, I said it as fabrication of silicon carbide wafer and its challenges and approaches. Again, my name is Jeng-Rong. I'm from National Central University, Taiwan. Okay, here is the contents of my speech today. First, I'll make a quick self-introduction and my current research focus. And then I will make an introduction about silicon wafer and the topics and some topics I'm working on and their results. Then I draw conclusions. And finally, I will leave about 5 minutes for question and for QAs. Okay, this is my quick CV. I think I can speak that. Okay, and skip it. Okay, my research focus is currently majorities on laser manufacturing technologies for semiconductor and electronics fabrications. And this slide highlights one of my current research focuses, which is the so-called laser pattern transfer. This technique enables the transfer of patterned solder paste onto PCB and LED electrodes for device bonding applications. So this is the quick steps. The first one is spreading, for example, solder paste on a transparent donut substrate, such as like glass, and then we adjust the gap between the donor and the receivers, then use laser to transfer the pattern on the substrate. So, for example, currently the feature size for our techniques, we can transfer like 15 diameter of 15 micrometers up to 1,000 micrometers. Then the substrate can be the PCB, glass, PI, PET, and ceramics. Okay, and this slide, we show the laser transfer of massive LEDs. And this technique can also be applied to transfer micro and mini LEDs. And actually, this technique is believed to be one of the most promising techniques for micro LEDs transfer. Okay, there are several photos showing the results. Here we use this technique to transfer solder paste and mini LEDs on different circuit boards. And this one is on PCB, often use the PCB. And this one is on flexible PC. And this one is on glass substrate. And excuse me, sorry. Okay. And this is on glass substrate, and this one is on ceramic substrate. Here we use the aluminum nitride, and because aluminum nitride have very excellent heat conductivities, so it can dissipate heat quickly. So it should be one of the potential substrate for LEDs. Okay. And my second current research focus is on laser processing on hard and brittle substrate, including glass, quartz, sulfide, and silicon carbides. And silicon carbide will be the primary focus of today's discussion. And this slide highlight one applications of glass substrate. And the key technique is a glass interposal. Glass interposals, and also glass core, and glass core substrate. So on glass, we need to drill in like 10,000, more than 10,000 of microdrills. We call this through glass vias. And on the vias, we need to do metallizations. Typically is copper on the holes as conductors. So actually, this is a very challenging task right now. And this slide, I just quickly show some laser patterning. And this one is a laser patterning modification on glass substrate. After this, we do like a etching to get rid of the modification portions and to get TGV. And this one shows laser inside cutting for different shape. And this is laser cutting and grooving and micro drilling on thin glass substrate. And this slide I showed the laser, the substrate is quartz, a thin quartz wafer, and the application is a high frequency quartz oscillators. And the thickness of the wafer is about 65 micron. So usually the thinner the wafers, the higher frequency can be achieved. And the machining challenges include we have to preserve single crystal structure without amorphous and twin crystalline defects around the surface of the holes. And we need to avoid any potential micro cracks and also achieve very low roughness. Actually, sometimes needed below like 0.5 RA. Roughness is less than 0.5 microns. And also we have to ensure a very small taper angle, usually less than 1 degree. So of course, the high speed drilling is the required capability. And for this case, we can drill one hole around 0.2 seconds. And this one shows sulfide, the laser machining on sulfide. And the applications is for Prof car, for IC testing. And sometimes we need circles and hole. And sometimes the requirement is like a square. So actually for square, drilling square hole through holes is very difficult. And it's very easy to get a micro crack along the hole surroundings. And if there are any like a micro crack and just a full substrate will like a break, like brittle, like a fracture. So sometimes we have to be very carefully to fine tune the processing parameters. And again, the table angle for all the holes should less than 1 degree, and of course maintain high-speed drilling capabilities are always requirement. And okay, finally, this slide just shows currently we have we established this one so-called 5G based smart factory for precision machining in NCU, and all this we development like a hybrid processing technique for machining like a silicon wafer, quartz, and PCD, and also sapphire and glass. All these are the cooperative companies in Taiwan. And for today's, I'm going to focus on this one, silicon wafer, and the majority, the major cooperated companies, Global Wafers, which is located. His headquarters is in Hsinchu, Taiwan. Okay, so I'll move to today's topic, an introduction of why we conduct the study of silicon wafer. And first, why SiC, then the process of SiC wafer. As we know, silicon, the gallium nitride and silicon carbide is usually called as the third generation semiconductor. And silicon-based semiconductors usually, silicon already has very successful in like information technology industry. However, its limitation is also very obviously because like high voltage applications or high frequency applications, the silicon-based semiconductor materials already shows problems. So we need currently we need the so-called third generation semiconductors, or the wide bandgap semiconductors, and the majority is silicon carbide and gallium nitride. And these two semiconductors can compensate for silicon's shortcomings, and so they are very promising materials after silicon. And with the emergence of new technology such as 5G and EV, electronic vehicles applications, the irreplaceable advantages of silicon carbide and gallium nitrides are accelerating the research, development, and application of related products, making the arrival of the third generation semiconductor era. And this one is for like a communication application, satellite communication. And this one for like a charging devices, and silicon carbide is the key semiconductor materials for charging of EV. And we can compare the properties of silicon, gallium nitride, and silicon carbide. And for example, application for high voltage, we can compare from three categories. One is high voltage application, high frequency switching, and high temperature applications. And this one, this area is the silicon. Actually, is very nano, and this one is gallium nitride, and it's higher. And the blue one is silicon carbide. We can see for high temperature applications, the silicon carbide with a very high melting point and also very high thermal conductivities. And for high voltage applications, gallium nitride and silicon and high frequency switching, these two, silicon carbide and gallium nitrides, they are the performance are closed. Okay, on the right chart, we can see for high voltage applications, you can see high voltage applications and also high frequency, and high power density. Silicon carbide is the best, so far is the best semiconductors. Oh, so as a result, silicon carbide-based devices has a very good performance in high frequency, high power, and high temperature applications. So it will be a very important semiconductor materials in response to like the developing and future high devices, for the power devices like and high speed communications devices. And this one, and this slide, I'm taking the process of silicon-based EV charging module as an example, and to show the module cost. Basically, we can separate into 4 phases. The first phase we call it glowing, crystal glows of silicon carbide. Then after that, we making silicon carbide wafers. Then the third phase is for device fabrications. Then finally is assembly and encapsulations. And the first 2 phases, we can name it as a front phase. Usually it costs like 40. Before it's even higher, but now it's the percentage of cost is reduced. And for the back, we call the back phase, it's about 60%. But for these 2 steps, 2 phases, the manufacturing technique, actually they are like stable and matured, very matured. So the key lies in silicon wafer fabrications. And why silicon wafers fabrication present challenges? First of all, the growth rate, the crystal growth rate is very small, very slow, and it's very difficult to achieving large thickness. Even so far, we can making like 8 inches, and actually 8 inches silicon wafer is coming, is supposed to be a very large mass in the coming years. But however, the thickness of growing silicon carbide is still very challenging. And also the slicing, polishing, and grinding are very time consuming and very significant consumable materials usage. So cost for time and grinding materials and consumables remain very high. And another challenge is to make the very thin silicon wafers, and thin slicing and excellent surface slicing techniques are still very difficult to achieve. So besides, there are also for equipment are not readily available. So it's still very open areas in silicon wafer manufacturing. And this is the steps showing manufacturing and silicon wafer. And the first is the growth, crystal growth. After crystal growth, the output will be like a ingot. Then the second step we need to shaping the ingot to cylinder shape. But like I just mentioned, the thickness of the is usually several centimeters. It's very difficult to grow thicker silicon wafer ingot. And then is a slicing into steps, into a piece, into pieces. Then is going to grinding, laving, and polishing. And after the last step we call CMP, which is represents as a chemical mechanical polishing. And after this step, the surface roughness is down to Armstrong labors and even sub-Armstrong labor. So after this, then we can do cleaning and inspection and packaging for sale. So this is quite a quick steps for flowchart for making silicon wafer. And my focus research highlights, this slide highlights my research topics on silicon wafer manufacturing. And I also I'm going to also present some of my findings in these topics. And for our research on silicon wafer manufacturing, the materials actually, the slide materials is provided by my cooperative partner, which is Global Wafers. And our work focus on several key stages, including ingot edge trimming, we call it shaping here, and then wafer slicing, and subsequent grinding and damping. And finally, is the polishing steps will is conducted in in GW, and more specifically, my research addressed ingot shaping, slicing wafers, and front trimmed cylinder, and grinding polishing for the sliced silicon wafer. Yeah, and also this portion. Okay, here I will introduce our in this speech. I will introduce our three main research focuses, and the first one is we are developing the so-called wire electrical discharge machining technique for shaping and slicing, and also the laser steel slicing technique. And the third, the topic is we are so-called we are developing a very fast and cost-effective. We name it as photon assist surface modification method. Also, so based on for the first two topics, because the mainstream method for shaping and slicing silicon wafer is use the so-called diamond wire sawing, which had the following issues. It usually a large curve width, more than like around 120 microns. So as usually in terms of material cost, it damages a lot of materials. And the surface damage on the slice wafers is large. You know, this is a schematic. We can see this is the diamond salt slice surface, and we can see there are deposit there after slicing, and also it will cause a defect there with a micro crack. All this had to be polished away because this one it will affect the later epitaxial process. So, okay. And so our approach, we are developing wire EDM slicing and laser slicing techniques for shaping and slicing. We can reduce the curve width and minimize the surface damage on the slice wafers. And we are also enabled to slicing very thin wafers. And for the third topics, the photon assist surface modification method. This method can dramatically reduce the silicon surface hardness. You know, for example, we can control the thickness of the modification areas from several micrometers to several tens of micrometers. And this one can accelerate the grounding and lapping efficiency. And that can effectively reduce the polishing cost. Okay, so then I'm going to show you some results. And the wire EDM, actually, this is a technique of the so-called non-contact machining methods, which is one of the non-traditional machining techniques that use the electrical energy and transfer it into thermal energy, so which then used to erode the workspace. Here is the silicon carbide. And so we use this machine, which is this is from Chamber. That's also one of my cooperative companies in Taiwan. So then we design special fixture for wire EDM cutting. Then we can see there are some photos. You know, so this one is for ingot shaping and wafer dicing and slicing. You can see there are electrical chargings. So locally, it's very high temperatures, so that the thermal energy can erode the workpiece. So after slicing, we conduct several measurements. Okay, there are some results. First, the curve width. In this study, we use the wire with a diameter of 100 microns, and the total curve width loss is only 106 micron. So the curve width, we can control it very small. And also for the ink and for the ingot slicing, and because the ingot is thicker, so the curve width loss is about 120 micron. And even this, which is much better than diamond saw, diamond wire saw technique. And the second one is the performance improvement is we reduce the heat affected zone. For this case, this is a slice surface. The heat affected zone is less than 10 microns. So this is very compared to wire saw technique. That's usually more than 20 microns. And this figure shows the surface roughness after slicing. We can achieve the surface roughness around 0.5 and 0.5 micron. And the total TTV, total thickness variation, is less than 12 microns. Actually, this one, compared to the all published or existing results, I think this one is these results are very competitive. And the second topic I'm going to show is laser steel slicing. And the principle of the laser slicing, firstly, we focus the laser beam, the focal plane, inside the silicon wafer. But usually the laser we have to be like picosecond or femtosecond lasers. Then we do modifications on the focal plane. And after this, we apply an external force. For example, like a tensile force or ultrasonic agitation. We can separate the two. We can separate the into two pieces now. And after that, we polishing the modification areas. Then we can obtain a very silicon wafer. And the advantage of the laser steel slicing, we can have even nano curve width, usually less than 10 micron, and very small, very minimal micro damage and heat effect zone along the slide surface. And this technique can fabricate very thin wafers, less than 100 micron thickness. Okay, so later I'm going to show you some quick results. And this schematic shows the laser processing. We are going like a zigzag pace on the focal plane. So after that, temporarily we use like a diamond blade and to scratch on the surface, then bend it into two parts. Then we conduct observations from this side and also from this side. Okay, so there are some results. Actually, first we observe it from this side. In this case, we show there are modification layers. Okay, this we call single internal modification layers, and sometimes we can achieve double modification layers just by one cycle of laser inscription. And to observe the modification layer more clearly, we polish it, grounding, polish the surface. So we can see a very like a bright areas. This is a laser slide marks. And for better observation, we etched the surface in KOH solutions. Then we can see a very clear laser slide layers. Okay, and the hitch of each laser scribing is for this case we take 8 micrometers. Okay, and if we observe from the second view, second direction, another direction, we also see very clear separation there. And again, this is after grinding. And we after etching, we measure the depth of the and also the width of the layer, and the width is about usually less than 5 micron, and the depth of etching depth is about several microns. And this is more clear SEM pictures. And the scale bar here is 5 microns. So this one actually is very thin. So I just mentioned it less than 5 microns. And this is 3 microns. It's also less than 3 microns. So we can make a very narrow curve width. And this slide just shows some separate the morphology of separated surface. And this is the trade of laser marking. As I just mentioned, the H is about 8 microns. And this is the top surface, and this one is the bottom surface. And sometimes, we can achieve like a double modification layers. And this one, we have, again, after grinding and the etching, we can see 2 layers during one cycle of laser modifications. And this slide shows from the different view angles from this side. The same results can be observed. Okay, and here are some SEM image. Again, you can see very clear after etching. You can see very clear, like a sliced area, sliced layer, and the thickness is less than 5 micron. Okay, then I'm going to move to the third portion of my results. Okay, this one, this method we call the photon assist surface modification, PASM. And this method, based on this method, we successfully reduce the surface hardness, very efficient, and that can accelerate the grinding and also reduce the consumables and time costs during grinding. So here's my okay, so I can see, okay. Take this one back. Okay. And after slice, the sample again is from GM, GW, Global Wafers Company. They slide the silicon wafers. The worst case is like this. You can see the diamond salt, the marks of diamond salt mark. And we got this. Then we do surface PASM surface modification. And this is a top view after surface modification. This is a side view. So after this, then we go to the grinding and we conduct the grinding and lapping test. And the main results, we can control, based on this technique, we can control the modification thickness from 5 micron to 30 microns. And the modification time usually is less than 1 hour. And the hardness of the modified layer reduced the 65% of the original surface. And the hardness from 4,700 down to 2,800. And all the modified area where we wouldn't introduce the new microcracks. Okay, so before grinding, we performed a pre-scratch test to compare the original surface with PASM modified surface to evaluate the effectiveness of the modifications. Here you can see just very quick. This one is original surface. We use very simple, mechanical way to scratch the surface, and because it's very hard and brittle, so it is easy to make a crack, and like separate. Okay. And this one is with and this one is with PASM processing. So see, we can scratch the modified layer materials here, very small portion, because usually the thickness of this layer is around 10 microns to several 10 microns. But sure, we can see there are materials scratched off from the surface. That means it's very soft. The surface is softened. Okay, then we conduct the grinding and lapping test. This is a quick flow. And the first is a silicon wafer, the original silicon wafer. So one we do without surface modification. We call this ACDRC surface. And the other one is with surface modifications by PASM. So then we conduct the grinding and also lapping test and compare the surface profile and surface roughness. Sorry. Okay, this is some results. We starting from the ACDRC surface, and this one without surface processing, is as the control group, and with the PASM processed as the testing group. Then we conduct grinding and also lapping. And the surface conditions, ACDRC, the roughness is about 0.2 RA, the surface roughness, and RG is about 1.2. And after surface modification, the surface roughness is very close, And then we conduct grinding. And for this case, we do the sample size is 2 centimeter by 2 centimeter. And for lapping, we conduct 6-inch silicon wafer. Because this one actually is kind of expensive, so we didn't conduct many experiments. So usually we do like a small samples. The normal size in my lab, we conduct 2 centimeter by 2 centimeters. And this one, I just show how we do the grinding test. Sorry. Now we use 3M sandpapers and fixed. And the samples is initially embedded. And the size is about 2 centimeter by 2 centimeters. And this grinder is for mechanical materials experiments. So that's a very normal machine, grinding machine. So then we place the embedded samples then applied the pressure, then conduct the part the grinding, and just use water, to assist to take off the abrasive away. After 14 minutes of grinding, then we dry the species, then conduct the surface roughness and thickness measurement. Okay. And then here are some results. For silicon carbide, they are both sides have different properties. One is called carbon side, the other is called silicon side. And usually the silicon side is more difficult to be polished. And this one is original surface morphology. After 10 minutes of grinding, you can see the carbon size is getting better. The silicon side, we still can see the scratch from the diamond saw, the line saw scratch. After 30 minutes of grinding, we already achieve very flat and very low surface roughness surface. And this one just quickly compare the results of grinding of 50 millimeters grinding, and the green line is the ASCAD samples. Initially, the surface roughness is about 0.2, 200 nanometer. Then after grinding, then we take off some surface containments. After that, 20 minutes, 30 minutes, 40 minutes, to 50 minutes, the surface roughness cannot reduce anymore. And the resulting surface roughness is 148 nanometer. And for our modified surface, the initial roughness is close to the initial surface roughness of the ASCAD samples. But we can after grinding, we can quickly reduce the surface roughness in 10 minutes. Actually, that's down to 20 nanometer. Then after that, keep reduced. The surface roughness keep reduced, and about 30 minutes, it reached the minimum surface roughness we can achieve, because it's about 5 nanometers, and the surface roughness cannot be reduced anymore, because the sandpaper we used, the particle size on the sandpapers limited the final surface roughness of the ground surface. After this, after grinding, we have to conduct like a CMP, mechanical polishing, with some chemical agents to polish the surface down to several angstroms or sub-angstroms levels. Okay, but anyway, from this modification, this results just quickly show after modification we can reduce the surface roughness very fast, because the surface, a large portion of the surface is softened, so we can erase polish away the surface very fast. And these figures compare the percentage of mass loss. So this one is ASCAD surface, and this one is polished, modified surface. So we can see, around 30 minutes, the material, we call this material removable rates, is So this one is about more than 3.5 times than the unprocessed surface. Okay, then we also conduct only two experiments for 6-inch surface silicon wafer lapping experiments. And this one, that's lapping wholly 6-inch silicon wafer. This is the process of polishing. And again, this one is pretty pressure, then we do slurry. This is diamond. The slurry is with diamond powders. Then we do lapping. And the slurry coming from here. Then we use water to clean the surface abrasive. Then dry the surface. Okay, this after 40 minutes of lapping. I said before lapping, after 40 minutes of lapping. And this one is unmodified surface for comparison. And we record the surface roughness. Then this one, finally, after 2 hours of lapping, so then we compare. This one is with surface modification. This one is without surface modification for two hours lapping. And because for this case, we didn't do any optimal processing parameters. So just a quick check for like an initial, very quickly to conduct our PASM measure on 4 6-inch silicon wafers. And because the slurry include diamond powder, so it can polish away, can lapping away the surface roughness, even the surface is without any modifications. So, but we still can see the surface roughness for for modified surface is much better than without surface modifications. And this table quickly show the results, and as cut the initial conditions and of initial conditions for ASCAD samples and PSM samples. Again, they are very close. But for 6 inches lapping, we also do in our laboratory for only 2 centimeter by 2 centimeter lapping. And this one we use silicon oxide as a slurry, and 20 minutes lapping, we can down to 0.6 surface roughness. Because this is conducted in my labs, so we already very familiar with this equipment. But this one, this is for 6 inches. We outsource the outer company to help us. So we didn't conduct any process parameter optimizations. And also the slurries is with diamond powders. So even the lapping hour is longer, but surface roughness is still higher for this case. Yeah, But at least we can approve after service modification. It's very easy to get the service roundness for, and also like micro cracks, removing for the next stage CMP process. Okay, so finally, I'll draw my conclusions of today's presentation. In today's presentation, I focused on manufacturing silicon wafer and highlighting 3 key technologies involved in the process: ingot edge trimming, cylinder slicing, and surface softening. And these techniques include wire EDM shaping and slicing, and laser steel slicing, and also photon assist surface modifications. And the major conclusions are as follows. For wire EDM shaping and slicing, we successfully achieved curve width around 106 microns. And for wafers, and 120 microns for ingots. And the heat effect zone on the cutting surface is less than 8 microns. And the surface roughness of cutting faces is less than 0.44 micrometers. And the second technique is laser steel slicing. We can achieve the curve with less than 10 micron. This is tremendously reduced of curve width. And heat effect zone and the micro crack zone on the cutting surface is also less than 10 micron. So that means totally we only need to polish it away about 20 microns. The material waste will be geometrically reduced. And this we also developed the double slicing technique. And that means we can slice we can achieve 2 slices just within 1 cycle of laser processing. And the wafer thickness can less than 100 microns. This is like a very promising for thinning, for manufacturing of thin silicon wafers. And the last technique we developed is a so-called PSM. And we developed a very effective surface soften hardness method. And we can reduce the surface hardness more than 50 micron. And usually, sometimes it's actually more precisely around 60 microns, around 60%. And these techniques can enhance the grounding efficiency and increasing material removal rates by at least 3 times. Okay, I think I'm ending my presentation here. And any question, please.
Okay, thank you very much for your presentation. Thanks.
Thank you. Hopefully you can. You're interested. Yeah.
Very interesting speech and questions. I suppose there could be some. Oh. Okay.
Thank you, Professor Hall. I'd like to ask about the PASM method, and more specifically about the light that is used to modify the surface. I suppose it's some kind of laser, probably infra. Can you please?
Sorry, there are some echoes. Can you speak a little bit slow so that I can hear more clearly?
Okay, I'm sorry. Maybe I will come closer to the microphone.
Yeah. That's better. That's better. Yeah.
Okay. Thank you, Professor, for your lecture. I'd like to ask about the PASM method and more specifically about the light source used for the modification of the surface. I suppose it's some laser, maybe in infra. Can you please tell us a little bit more about the modification itself and the light source for this?
Okay. Actually, there is a no. We are filing a patent. A patent is pending. Because at the beginning I used laser source, but later I find that the laser source is kind of expensive, for these applications. So I try to find to take another alternative light source. It turned out to be very cheap. So like I can use LED sources, and so now I think this method we can modify the large area surface very quickly. Like in my lab, it's less than 1 hour, but commercially application in the future, I believe it can less than maybe just 0.5 hours. But I'm sorry, I cannot tell you what kind of source I'm using right now. Yeah,
understood. Thank you.
Okay. Okay. Any other questions?
sorry.
Okay. Maybe sorry for this inconvenience. I expected we will have the ordinary microphone.
Okay, yeah, very interesting. I wonder if you have an insight what happens when you modify the surface with a laser and it leads to the decrease of the hardness. Like if you have an insight what happens to the material.
Okay. You mean after internal modification, right, by laser? Usually, the purpose, the application of laser is to break the SiC covalent the bond. So after laser processing, laser treatment, the silicon carbide chemical bonding is broken. It's broken. So the layer there, the strength, we just need. It actually is less than 100,000 strength compared with the original strength. So it's very soft surface. If we process this in air, it should be a silicon oxygen, but inside the silicon carbide, it's just the broken of silicon and also some carbons.
Okay.
Yeah.
Okay. Any other question? No. So, well, yeah, you are just on time. Thank you very much.
Thank you. Yeah.
Thank you very much.
Yeah. Thank you.
And
Thank you. Yeah.
we will be happy if you will stay with us and to listen the other lectures. So
yeah, I will for 1 hour, but later I'm going go out for dinner.
Okay. Thank you very much.
Thank you. Yeah.
And now we will proceed with next lecture. Okay, for the online attendees, can you see the screen? Could you reply, please?
Yes, it's okay to me.
Okay. Okay. So the lady next to me is Dr. Hospodková from Czech Academy of Science. Very pleased to have you here. And Dr. Hospodková is working at the Institute of Physics, and her professional work is devoted to preparation of semiconductor epitaxial layer by metal organic vapor phase epitaxy. She specialized on the preparation of quantum wells and quantum dots nanostructures in semiconductor material system. She concentrates on design and preparation of structures containing highly strained structures and many other activities. Suppose we will go for the lecture. So yeah.
Thank you very much for kind introduction. Thank you for giving me the possibility to give a talk here. I hope they can hear me. I don't need to have any microphone or, okay, shall I be somewhere near here?
Yeah.
Okay. So, and my presentation will be more concentrated on gallium nitride because I'm a gallium nitride grower. I will be my specialization in metal organic vapor phase epitaxy. But we can also make some comparisons, some part of the presentation with silicon carbide. Just a bit, as you. Okay. It doesn't work.
To má teda jako spuštění, jsem zjistila. No, tady má šipkama, tak šipky doprava doleva. Ono se to možná...
So this is what already Professor Hart showed you, and pentagons which you have seen many times in literature, comparing the basic or the most industrially used semiconductors, which are at the moment silicon, of course, silicon carbide and gallium nitride. So from the comparison, you can usually see that silicon carbide, whereas the strength of silicon carbide is thermal conductivity. Gallium nitride is supposed to have better higher breakdown voltage, but this is not so. This cannot be actually so well used because we do not have a real gallium nitride substrate available. So if we compare, for instance, here is a hexagon where we compare the properties of these two materials and with silicon. So for, again, as we told, thermal conductivity of silicon carbide is great advantage. And suitability for high power application comes also from here and also from availability of substrates. Then high switching performance for and high frequency applications. For that, the gallium nitride is much better. You can see here, and for high voltage, the breakdown voltage is better for gallium nitride. But since the gallium nitride substrates are very expensive, and you do not have the homologue epitaxy, you cannot use this advantage actually. But there are also some other of the application fields which we didn't talk about yet. There is also others because the bond between atoms in both type of semiconductors, gallium nitride as well as silicon carbide are very strong. It means that you can use them also for detectors or for electronics in environment with high radiation because they have radiation resistance against the radiation. the biggest advantage of gallium nitride is direct bandgap, which opens many applications like LEDs, white LEDs, which we are using, UV LEDs, which are now under development, and also some detectors are works better. Detectors of light or ionizing radiation work better in case of direct bandgap. So here is the family of semiconductors. Here we can see the silicon carbide, which has a quite similar lattice constant to gallium nitride, and is only a little bit has lower bandgap. But the advantage of nitrides is that you can make heterostructures and prepare structures with different functionalities. You can make quantum wells for electrons, for holes, and so this brings you can prepare laser structures like this and combine different materials in one structure, which has then design functionality. So this is something what is unique to nitrides, and silicon carbide or silicon do not have this possibility. So this is, by my opinion, the biggest advantage of those materials. That's why they will have, all of them will have its field of application where they cannot replace each other. Let's look to the availability of substrates. Both materials is difficult to prepare as a bulk. But silicon carbide has better position, and you can see it on the price. I'm not sure if these are, because this is it's not open usually on the internet. So if it's for, when we ask for a quotation, we have got this these numbers. So silicon carbide, 2-inch silicon carbide, we could buy for $770 US, while 2-inch gallium nitride for 2,800. And with 10 times 10 silicon carbide and gallium nitride, it was even more ridiculous. So you can see that availability of gallium nitride substrates is still difficult. So we are using usually different substrates for the epitaxy. It could be either silicon or silicon carbide, or most often sapphire. And now let me tell you something about our laboratory. At the moment, we have 2 MOVP apparatuses with different design. One of them has, the white one has vertical reactor with cold overhead, while the other is older one with radio frequency meter, and the reactor is horizontal. The white one with closed copper shower head, maybe I don't have now here I'll show you later. It's something like a shower and has high memory effect. So we combine these both apparatuses for different applications. For hand structures, the white one is quite okay, while for luminescent applications, we are using only the blue one, because the structures from these apparatus are much more clean and have better properties. What we are doing at the moment, we have several topics, scientific topics on which we are working. One are fast scintillators, where we have collaboration with Gritur company. Another very interesting is our vacancies in gallium nitride, indium gallium nitride, aluminum gallium nitride, and heterostructures. On this topic, we collaborate with the Faculty of Mathematics and Physics, and also with the samples are measured at Rosenberg in Germany. And we have a really interesting results about vacancies in epitaxial layer. These results are quite unique because usually they have only available information is about thick substrates, because it's measured by positron annihilation spectroscopy and it penetrates very deeply into the material. So we have really unique results. This is not a topic of this talk. And then we work on HEMT structures, because you're usually high transistor people, electronic people. So I will show you the results about this topic, although it's not our measure. We are more on the scintillators and vacancies. And now we are opening a new subject of research, which are nanorods for water splitting, made from our kosher nanorods or in-gun nanorods prepared by bottom-up or top-down technologies. So this is what we are starting, and we also start developing UV light sources. So, and we will see what will be. So usually what we use as substrates is sapphire, as majority of people who are working on light emitting devices. Sapphire is very good for that. There is nice developed technology to suppress the density of dislocation, although the strain is not ideal, and also the thermal coefficient of thermal expansion after the growth. If you go down with the temperature, you develop some curvature of the substrate, which we have to manage. On these substrates, we have developed two methods where we can produce either structure with high density of dislocation or structures with lower density of dislocation. It depends on the temperature profile during the growth, and if we have a coalescence, these are Fabry period oscillations. If the Fabry period oscillations, when we grow gallium nitride on sapphire, start too early, then it means that you develop a high density of dislocation. While if you get a coalescence layer thick, so the surface is rough, and then the ions coalesce after some time, the dislocation have time during the growth to curve and annihilate with each other. So in this case, we have a lower density of dislocation. And this I will show you later on how we use it to study the effect of dislocations on different properties. So it's a nice thing to know how to produce both samples. What we are using is trimethyl triethyl gallium. Triethyl gallium in nitrogen atmosphere is usually used if we want to grow indium gallium nitride samples with trimethyl indium. For argon GaN, trimethyl gallium is used usually in hydrogen atmosphere. And this is the closed copper shellhead. You can see it's almost like a chimney because you have to vacuum clean after each grow the carbon which is deposited on the shower, and these small pits are holes through which the metal organics are coming into the reactor. So it's quite a dirty process. I would say there's a lot of carbon, but still it's not so much incorporated into the layers. Concerning our topics, so the first topic which we started to work on in our laboratory is fast scintillators. So these are many quantum well structures of many quantum wells. For some applications, could be even 100 of them. And the scintillator is material to which, if the ionizing radiation comes into the structure, it responds by emission of light. But it has to be very fast because those scintillators are developed for little company, for electron microscopy, or for other applications like time of flight detection of gamma rays, or of in a SIMS measurement of ions. And for instance, for electron microscopes, as you know, we are in Brno, so electron microscopy is some like capital of electron microscopy or surroundings here. So electron microscopes are nowadays necessary for inspections of integrated circuits. Each integrated circuit has to undergo 20 times the inspection under electron microscopy, so that the production is not slowed down by this inspection. You have to have very fast working electron microscope. And something what makes them slow is a slow scintillator, which is detector for secondary electrons. So they need very fast detectors, fast scintillators for that, which can just blink and then stop the shining, so that they can scan fast. For that, nitrides should be fine, but it's not easy to do it. And also from some top pad and top SIMS applications where you have to have a very fast rising time. So it took us quite a lot of time, some years, to develop. Here's how we started, and then we moved to I would say a shorter wavelength, but this is not the main development. The most difficult thing was to get rid of any defect bands in our material, and to have very fast excitonic luminescence, which is fast, which is very fast. This month, we hope we are we reached this goal. So hopefully, already our structure will go to production. Another thing which we work on, which we started to devote our attention, are nanorods. Nanorods, and with the aim either to go to very fast scintillator structure or to go to water decomposition to hydrogen and oxygen. The main idea is that the indium gallium nitride has a very nice position of conduction and valence band, which is in around 35% of indium. It should be almost perfectly adjusted to oxidation and reduction potentials of water, so it can split the water photocatalytically. It means that if you absorb the sunlight. If INGAN is absorbing the sunlight, it has available electron and hole, which can enter the reaction and give electron to the water to make H3O plus and then develop hydrogen and to reduce oxygen from the water. So this is quite interesting thing. There are not many materials which have this property actually, and INGAN is unique. The problem is that to grow INGAN is very expensive. So we are just looking for some less expensive ways how to produce them with a Korean partner, which have some ideas how to make these crystals more easy to grow on big areas. So here are some of our nanorods already. This one nanorod has a spore shell already with GAN and INGAN on the shell structure. You can see that there is a gradient in composition, which actually would help to separate electrons and holes, which is necessary for us, for if you want to use them as for water splitting. Another core shell structure with multiple quantum wells around. There are 10 quantum wells around GAN nanorods. And here is the measured decay time of such structures. And you can see here's GAN exciton and nonpolar quantum wells, which are very fast. I mean, here is 0.2 nanoseconds. So it's less than 0.1 nanoseconds. So these are would be extremely fast structures. And this is the polar quantum well. It's still quite fast. It's below 1 nanosecond, but these non-polar, which are on the side of nanorods, are even more, are even faster. I'm not sure if maybe the auditorium, if you know that the gallium nitride is a polar semiconductor, and yeah, okay, so I don't have to just wasn't sure. Okay, so and the next topic are some high electron mobility transistors, on which we also work, but this topic we at the moment we do not have a project on it, and we keep it just to educate students, for instance. So they do a master diploma works on it, and I think it's good to keep it if we have some expertise in it. So yes, here the nitride with respect to silicon carbide has advantage that we can produce heterostructures and that it is polar semiconductor. So in polar direction, the argon-GaN interface on the lower interface of the argon barrier, there is an electric field which causes, if this part of conduction band goes under the Fermi level, it's filled by electrons, and we get very high two-dimensional electron gas with quite high concentration of carriers, which is typically 10 to the 13th per square centimeter. And there are so many carriers that they shield the electric field, which is around ionized impurities in this area. That's why we get very nice and very high mobilities of electrons in this region, which in our sample the best are around 1,800 centimeters per turbo second in Australia. What is also a nice property of two-dimensional electron gas is that we have independent on temperature the concentration of carriers, which is not typical for any semiconductor structure. So this is interesting. Here the resistivity is, of course, with increasing temperature increasing and mobility is decreasing, but the sheet carrier concentration remains the same. HEM structures are usually not grown on sapphire as luminescent devices, but usually either silicon or silicon carbide are used. Silicon because they are it's very cheap and it makes it compatible with silicon, partly compatible with the silicon technology. And the silicon carbide brings advantage of good thermal conductivity and quite acceptable and quite good lattice constant mismatch. And also the bowing of growing gallium nitride and silicon carbide is not so difficult as in the case of just silicon. So we have tried first the traditional methods to produce gallium nitride on silicon. So we have developed technology on silicon and silicon carbide. On silicon, it was quite tough for us, and we couldn't get a nice flat surface by. You have to grow aluminum nitride, not to etch a silicon by gallium. So first, aluminum nitride is grown. You get nucleation, coalescence layer, and then you decrease the algan towards GaN, which helps to also to manipulate with bowing after the growth. But unfortunately, here we were not successful. We have got a terrible surfaces and couldn't help. After many attempts, we didn't get into the goal to get a flat surface. Then we developed a different way how to grow gallium nitride on silicon by aluminum nitride nucleation, and then we grow gallium nitride on it with silicon nitride layers decreasing the concentration of dislocation. Aluminum nitride layer to manipulate the bowing. Again, silicon nitride to even more suppress the dislocation density, and again, aluminum nitride, gallium nitride, and then we went to quite a nice surface. So this is now our preferential technology to grow gallium nitride on silicon surface. On silicon carbide, it was also not easy, but probably because of the quality of silicon carbide surface before epitaxy. Because when we use the fast nucleation with I think aluminum pre-dose, after metal aluminum pre-dose, we get quite a good results, but not on we had to use a special commercial silicon carbide substrates, and then we get quite a low temperature. So I told you before that we can grow buffers with different dislocation density on sapphire. This we have used to grow structure on it and see how the dislocation density can affect the properties of structures. Here are different samples with different dislocation densities, which we have used as templates. And on these templates, we then do structures and see what will happen. So we have from 10 to 6, 3, 10 to 6 on when we go on GaN substrate, over 10 to the 8th, 10 to the 9th, towards 10 to the 10th if we grow a high dislocation density on sapphire. What happened? What was that when we grew the hand structures on it, surprisingly, the highest sheet hole concentration which were measured on our structures were for those samples which had lower dislocation density, but the mobility was worse, much worse than in case of growing on high dislocation density or the middle dislocation density. So what happened was that in case of low dislocation density, the carbon dope layer, which was used to make high resistivity layer and to separate GAN channel from the bottom part of the structure, which is deteriorated. This C-dope layer didn't work actually. So we had to add something more. And we have decided to grow not the superlattices as it's sometimes used in the industry, but for easy way, we have put their algan-back barrier, which is more easy, and found that it can work also well, but we have to be afraid not to produce another two-dimensional electron gas under the algan-back barrier. Had to find proper parameters to achieve good results. That's why we have prepared several set of samples with different percentage of aluminium in back barrier, thickness of back barrier, and also different thickness of GAN channel layer. I'll show you. So, as I told you, we had to take care about this second two-dimensional electron gas under the back barrier. And you can see that if we have too small concentration of aluminium, the separation of back barrier from the bottom part of the structure is not sufficient. So electrons can penetrate there, and we have very high sheet carrier concentration, very low mobility. But in case of optimal concentration of aluminium, we get quite high mobilities over close to the 1,500 and reasonable carrier concentrations. The same was with the thickness of algan-back barrier, where we have used optimal thickness was around 40 nanometers, with the best results achieved on the mobility. Again, too thin layers. In too thin layers, some carriers still feel or can penetrate in the bottom part of the structures. What is interesting that the back barrier doesn't work at all, almost for high dislocation density samples. It works only in case that you have low density of dislocations. And GAN channel layer was even more interesting, and we we're not sure why it is. Here are some measured from CV measurement. We can see the channels. Here, this is under the two-dimensional electron gas under the algan main barrier, and here are some electron concentration under the back barrier, but here are several orders of magnitude lower, of course, than the main part, and still it works well, much better than if the algan-back barrier is not there. Before, we also tried some graded algan-back barrier, but the results were not perfect. Not sure, not know exactly what was the reason why the Allenberg barrier didn't work, because there shouldn't be any two-dimensional gas under it, but probably it was somehow leaky for electrons to get. Here are measured Hall mobilities for the structures which were the green are those which had lower dislocation density, and red samples had higher dislocation density, and these are all the samples which we have measured, and you can nicely see that there is a really difference between samples with lower and higher dislocation density. So it makes sense if you want to make a high frequency application to use silicon carbide and to go to a lower density of dislocation if you want to have a good performance of your transistor structures. So it's really important. And I skipped when I talk about gallium nitride that we also the channel layer. We have also tried to improve the technology of the channel layer. And here we have found a very strange and surprising effect. Normally, you would say that the channel layer and the interface between gallium nitride and aluminium gallium nitride barrier should be perfectly flat. But unfortunately, we have observed that with flat surface, we always get a worse performance, worse mobility. And it was really interesting. And if we grew a VPIT on this interface, we get better results, better mobility. So we were quite surprised why it is. You probably know that VPITs can help, or I don't know, in quantum wells in performance of it, that the intensity of luminescence is increased. And there was a nice article about it of a Hangleiter, that VPIT, if a quantum well is deposited on VPIT and flat surface, on a flat surface the quantum well is thicker, on VPIT surface it's thinner, so electrons are actually protected they cannot enter the region around this location, which is deteriorated, where around this location you have always a lot of defects, and if you have VPIT, which is always formed around this location, especially with screw component, then electrons do not penetrate into this region because it's a barrier, an energetical barrier for them. They are separated for this, and the luminescence is enhanced. But could this be also in HEM structure, something like that? Here we have a deteriorated region around this location. And we put, if we suppose that there is a VPIT around on the interface, and František Hayek has calculated on the next nano software, we could see that in that case, electrons, here is electron concentration in two-dimensional electron gap. To go close to the VPIT is for electron also a barrier. So electrons are mostly in the flat region, not entering the VPIT, because there is semipolar semipolar facets with a lower depth of quantum well. So electrons do not penetrate this region around which is deteriorated and go around actually. So it's surprising that not flat surface can help to improve the mobility of electrons if the interface is like that. How to produce it? It's easy. You just can grow from triethyl gallium and nitrogen atmosphere. And nitrogen atmosphere VPITs are formed we have checked it. We always made 3 structures. Everything was the same. We only changed here the pipette on the structure and flat interface, and you can combine, and you can see here that in comparison we always get better hull mobility in case that we have a pipette. We have proved it for both, for structures which have higher dislocation density and lower dislocation density. I thought that higher dislocation might not work because there will not be enough flat space around, but it worked even for those structures. And I would say I'm pretty sure that it is because of the pipette, because we have also sent the structure for SIMS measurement and measure the carbon concentration. Here is the channel region. Here's Algan back barrier. Here is Algan main barrier. So somewhere here should be the electron gas. This is caused by the this deterioration or the change of the signal. And you can see that for high dislocation density, we have considerably higher carbon contamination. And although the carbon than in a low dislocation density, and although we have a higher carbon contamination for pipettes, if we have pipettes, than if we do not have them, still the mobility is higher. So it's really probably the effect of pipettes. This is how it looks, the surfaces looks when we made a stop growth and looked to the surfaces. You can see that the dislocation density has also a big impact on the morphology of different interfaces. So lowering dislocation density is a really good way to. And we also changed the size of pipettes to see what size you need to improve the mobility. And we have found that around 70 nanometers, it's quite okay, which was achieved in a thickness of GaN layer about 140 nanometers. So interesting. We also did some EM structures because the EM structures are fine and easy to produce, but it's not preferable for application because you have always open channels. So you have to have a channel which is normally off and then switch it on by the applied electric field or applied voltage. The most industrially used method is p-type doping on the top of the Algan, introduction of p-type layer, but this is done by magnesium. It brings some problems, for instance, with magnesium, which is penetrating, it's very diffuse atom actually, and it's problem to keep it only here and not to penetrate into the GaN channel, which would deteriorate the properties of transistors. So we have again done the structure with those pipettes as we used to. Put gallium nitride doped by magnesium on the top and separated the 20 nanometer gallium nitride undoped and looked by SIMS what happened. And we were quite lucky, or this result was good. Magnesium was not penetrating into the channel region at all. And we have proved it also by this, that we have etched down the top layers, get rid of the effect of magnesium and open the channel again. And after the etching, I don't know if I have it here. After the etching, the mobility was really very high, so magnesium was really not present in the channel layer. Another possibility how to prepare EM structure are ingot layers on the top instead of magnesium doping, because we thought if there will be a problem with magnesium penetration, ingot doping could also help to solve this problem. Another problem is, another thing was also a motivation, was to produce two-dimensional electron whole gas, which could be present on this interface. And maybe some logic surface or something like this, logic structures. So you can see here from the simulation that in a proper thickness and proper concentration of indium in capping layer, you can produce whole gas instead of electron gas and switch off one and or the other by applied field. So it could be also interesting for some logical applications. After etching, also in the ingot layers, the mobility was very high. The problem with ingot layers is for us the deposition of the dielectric on the top. We're using aluminum oxide, silicon nitride, silicon oxide, but all of them are leaky and not really perfectly working. So the under the gate, the diode is under the gate is the most tricky part. Here are some structures we use circular geometry for our transistor structures, which are done in the frame of the Masaryk, and you can see that the hem structures are quite okay. The hems are also nicely breaking. These we are going now. Now we are going to conclusions. So, and hem structures we developed the back barrier with proper parameters. We have shown that the mobility for mobility it's essential to have really low dislocation density. That the PPID morphology can increase the mobility, which is quite surprising, and the optimal size of PPID is 470 nanometers. And to say in a summary, I would say that silicon carbide and gallium nitride do not, they are not competitors. They are more semiconductors for different applications, GaN for high frequency, and if also for high power. Silicon carbide, because it has its own substrate, is perfect for higher power applications, high voltages. So I hope and they can even collaborate on each other by growing one on the top of each other. Gallium nitride and silicon carbide can add a high thermal conductivity to gallium nitride. So this is here it's shown that for 5G communication, gallium nitride is often grown on 4H or 6H silicon carbide substrate. This is our nitride team, and thank you very much for attention.
Thank you. Thank you very much for your kind presentation. Questions? I suppose there could be. No gallium nitride, of course, onsemi.
Thank you so much, Alice. It's a great presentation. The PPIDs, very interesting thing regarding improvement of the parameters. So there is optimal size of them, but there must be also some like upper limit where if you have more, but like is there optimal quantity, like density of these locations and density of the beacons? Because if there are too many, then probably lose your tech. Right?
Yes, exactly. So you can losing. We cannot adjust. We have two possible what we can produce, or almost two possible dislocation densities. So by dislocation density, we cannot study it. Actually, you can do it by increasing the biped size, and there are over the 100 there was slight decrease already. But actually, when we grew it on the high and low dislocation density, I couldn't see, there was always improvement with bipeds, which was surprising. I expected that there will be already suppressed, but it was improvement in mobility. It was strange. I do not have more study on this. Yeah. So sorry for that.
Still a lot of work to do with GAN.
Yes, but yeah, on the hand structures we now do not have a project. So if we do not have money, we cannot produce on it more work. So.
Maybe onsemi would be interesting to support.
A follow-up question. It's a very nice to do. So the VPs enhance the mobility, but how about the vertical breakout? Try to push it.
No, we didn't measure it. But yeah, this is not for vertical. I would say that this would decrease. This would be harming. It's only for the transport in the horizontal direction. Vertical properties, but it's bigger. I suppose it.
Okay, thanks. And concerning the hand structures, are you considering studying on nitride for the barrier?
Would be interesting. Yes. Thought about it, but I don't have money now for hand structures, so we have to consider the we're writing a project. So if we will have a project, if we will have money, I would like to for sure to try this.
Very good nitrogen. You have to magnesium on the top, gallium. You do magnesium.
Yes.
In the top, what is the role of this two magnesium in the quality of the gallium?
What is the quality of?
What is the role of this two magnesium? What is the intention of the two magnesium on the top of the
I'm not sure if I catch the question, but when we go on the top of the magnesium on the top, we produce the hand structure, but the hand structure it didn't decrease the quality of the structure below. Magnesium didn't penetrate into it, as I showed you by sinks, and also when we etched down the number, and again measure the mobility, it was very high. It was 1,800 something centimeters per second. So it's the quality stayed good of the hand structure. So it didn't harm to the channel.
Okay.
The essential was 20 nanometers of separation layer of the doped structures to our value.
Okay. Are there any questions? Maybe we have. Okay.
Sorry,
Yes.
I'm not any kind of material science guy. I but anyway, thank you for the nice talk. I have a very easy, maybe silly question for you. According to the parameter optimization, is it possible to do some kind of preliminary theoretic study, for example, derive some equations to predict the best, then do some kind of testable measurements to verify the theoretical results?
Yes, we have an external program where we simulate the structure and the properties of the valence band, on valence and protection band, on the concentration of predicting concentration of carriers in different part of the structure. So this we are doing, and according to this, we are adjusting the parameters. So it's just not attempting trying different composition, but first we calculate, suggest what should be the best, and then we are going. That's right there. This period. But we do not have any simulations for real transistor. We do not have available that. So, possibility, financial possibilities of our group. So.
Okay, AI help. Can you apply AI to speed up the process?
Yes. Well, no, AI helps me.
Okay. So we are running out of time. So thank you very much once again for your presentation. And I think that there will be a lot of discussions during our breaks, but let's proceed for the next speaker before the lunch. I hope that you are still fresh, because we will continue with the next presentation. Okay. So the next speaker is man, I am really happy we have Professor Humlíček over here, because I really appreciate his work and the thing he did during his really professional life. Professor Humlíček is a professor at the Department of Condensed Matter of Physics at the Faculty of Science, Masaryk University. He gave a lot of lectures at many universities related to fine band gap semiconductors, and I'm very happy he's here to give his talk on this topic. So, Professor Humlíček.
Thank you, Libor. So we will focus on a very specific topic of optical properties of mostly 4H silicon carbide. You can guess what the 4 objects here are. We will see short comments on this. The outline is as follows. I will remind you of the electromagnetic response at pretty high frequencies, optical frequencies. I will review very briefly the crystal structure and optical and isotropy of the hexagonal modifications of silicon carbide. And then we will go through the response, which are determined by just the lattice vibrations and free carriers at low frequencies. The frequencies are still very high, but relatively low. This is, let's say, for the energies below 0.4 electron volts. That is the frequency of 100 terahertz. We will see some low energy excitations seen also by Raman scattering. And then we will switch to the interband electronic transitions at high frequencies. This is ultraviolet range with the frequencies at the petahertz range. And there is, of course, a transparent range between the two.
low frequencies, phonons and free carriers, and high energy is the fundamental electronic response. We will see some interesting features of these optical response in mostly in doped and type 4H silicon carbide. And I will try throughout to show you the optical techniques or optical spectroscopies as good diagnostic tools. And I will also spend some time on the differing. We have already seen in the first lecture the basics. So let's see. 4H is the preferable modification for power electronics, wide bandgap, and so on. We have here the large saturation velocity in silicon carbide, for example, and all of the virtues of different materials are summarized here in these figure of merits. There are several of them, and 4H excels against silicon in all of the three listed here. I guess it's not necessary to discuss it further. So we will have to understand what quantities will appear here as the results of measurements and as the results of our interpretation of them. The basic thing is the polarization of matter at optical frequencies. Just moving the charges inside the materials by optical field. The movement is very typically asynchronous. We have the force, electromagnetic force, which tries to move the charges. The charge is really, but with shifted phase. That means what we need to understand is just the magnitude of these shifts, of these movements of charges, but also the phase shift. And the natural thing to use here is to use complex numbers, which have magnitude and phase. I will show you on several occasions spectra with real and imaginary parts of the response functions. The response functions are there are actually two very basic response functions. The first one listed here is the permittivity, which is complex. It has a real part. We are usually thinking of permittivity in terms of the capacitance of the capacitor. And another one is the conductivity, or its inverse, which is resistivity, which is the proportionality factor between the current density here and the electrical field of the optical wave. So these are basic relations between, let's say, the two basic response function. Here, the dielectric function, which is the complex, which is the complex permittivity here, the real and imaginary part. The conductivity I have shown, but in dealing with the optical fields, we need, of course, the refractive index. This is also complex quantity with the real and imaginary part here, and it determines the refraction and reflection of light at interfaces. I will skip discussing the negative inverse of dielectric function, which is good in seeing the longitudinal excitations in beta. Silicon carbide. We are very up in the periodic table. We see also the possibilities of doping here, just changing the numbers of electrons in producing free quasi-electrons and holes, another type of quasi-particles here. This is what I have shown on the title page. This is the crystal from onsemi Rozhanov in 2021. We have about 4 years of, I hope, fruitful cooperation in studying silicon carbide. These initial crystals were contaminated by 6H, which is unwanted. We usually deal with wafers which are of really high quality. Nowadays, it's mostly 8-inch material. The typical wafer has a miscut from the basic crystal orientation of 0.001, which is 4 degrees, and this leads me to the uniaxial anisotropy of hexagonal silicon carbides. We have here the, let's say, basic cubic structure, which is here shown in using these hexagonal planes, and it can be altered by changing the sequences of these 3 layers, and we have here 2H and 4H. 4H is the preferable material. It's just the stacking sequence ABAC. And this produces the optical anisotropy. The polarization is different in plane, here horizontally, and vertically out of plane. Let's start with these low frequencies, just the motions of charges with relatively small frequencies. There is a very nice picture, easily understandable, which is the approximation of bond charge model. This is the basic structure of 4H, and we have here the sketch of planes which are deformed under the optical field, and the lattice vibrates, and the basic classification is according to symmetry. The symmetry group is C6V4, which has the phonon representation of the Brillouin zone, which is reducible. I've seen here students which were obliged to understand this. The reducible representation splits into the in case of 4H in 4 vibrations with the symmetry A1, E1, E1, and E2. Sorry. And we know that A1, E1, one-dimensional irreducible representations, they mean the vibrations along the optical axis vertically, and the two-dimensional of the type E are in plane. They are two patterns of atomic movement in the planes with the same frequency. So there is also a vibration which is not seen either in infrared or in Raman. So the basic picture of the vibrations. We have here the high symmetry directions in the brilliant zone, and the long wavelength vibrations here in its center. It's called gamma, and these are frequencies of these normal modes, of the very basic highly symmetric vibrations, which we can see using optical spectroscopies. The frequency here are shown in wave numbers, which is the typical quantity used in infrared and Raman. This is just the number of waves per 1 centimeter in space. So the strongest of these vibrations is at 797 wave numbers here, which is about 24 terahertz. And we see the strong dispersion of these frequencies within the brilliant zone. And now, this is the first of my examples of pressure data. This is our reflectivity, nearly normal reflectance on an epitaxial sample. This was called by onsemi Rojanov as 29 microns. We have found that the actual thickness was a bit smaller. This is, I guess, easy to understand here. We have here the frequency in wave numbers. This wave number here is this 24 terahertz frequency of this basic mode. Very prominent feature in these reflectance, because the reflectance itself reaches almost 1. Between the TO and LO frequency here, the reflectivity is very high. It's called Reststrahlen band because it's the light which remains in the reflected spectrum after the reflection. The other frequencies are suppressed here. And we have here a nice pattern of Fabry-Perot interferences due to the differences in the response of the films and substrate. It's seen well below the TO frequency and also above here for higher frequencies. This reflectivity itself is really sensitive to the quality of the surface. This surface, the ideal surface, should reflect 100% of the incoming intensity. It does not, mainly in cases when the surface is not highly. Here we have several spectra of relative reflectivity. It was taken as the ratio between the reflected light from several samples and the light reflected from a very good epitaxial surface. And this tip here actually shows how much the individual surfaces are damaged. In this case, it's mostly subsurface damage because the surfaces themselves are, after polishing and polishing, they are very flat. They show only small variation of AFM.
University of Sheffield.
But we see that the actual material below the surface is damaged. So we have also ellipsometric data, which are very, very good because they provide that each photon energy, they provide two real numbers. This is what we need for the optical responses. The basic picture of the ellipsometric results is that are the pseudo-dielectric functions. We just assume we have a half-infinite ideal material below the surface, and we plot the real and imaginary part of the dielectric function, complex permittivity. The spectrum of the real part is here, and the imaginary, we call it absorptive part. They show very clearly the strong vibration at 797 wave numbers with very large peak values here, or the peak and tip here in the real part. This is plus minus 500 here, which is strong for the permittivity. And we have also some undulations here because the sample is 4 micron area. That means it does show the interference pattern here, but it's strongly suppressed at this scale with the large numbers of permittivity here or large absorption here at the TO wave number frequency. So the next can be refractive index. It's also complex. Is the square root of permittivity. And we have here the range around these TO in our sample is derived from our ellipsometric measurements of vector layers. We have here the usual refractive index. You will remember 1.5 for typical glasses. We have here the scale which goes up to 20 upwards, and it actually continues to be even larger. And we have also the real part of refractive index here. This is the blue curve, which is well below 1. That means that the phase velocity of this light is much larger than c, than the speed of light in vacuum. There is no controversy in this result because what we really can only observe is the ocean, and this is quantified by the group refractive. And this quantity, of course, is always larger than 1. And the group refractive index, this is this curve below the TO, and this is above the LO. Here you see it's above about 2.5 for H silicon carbide. This might be a bit surprising for people not working in infrared. The infrared response in good infrared oscillators, the response is really a sort of unusual. There is also a hint that we should lose the interference effect here because of the very large values of the group refractive index, which makes the interference pattern very dense, and the spectral resolution of our instrument is not good enough to see it. This is also what is observed here. You see, here the amplitude diminishes, and there is almost nothing to be seen here, in spite of the actual Fabry resonance in this. The instrument is not able to see it because of the finite spectral resolution explained here. Now, back to the 4-micron layer. Once again, we see the pseudo-dielectric function. We see the Fabry-Perot response of this epitaxial structure. The information contained in this is actually first the layer thickness, and second also is compressed in 3 carriers in the layer and the substrate. Now, the switch to large frequencies, large optical frequencies, which produce the so-called fundamental optical electronic response. We have here the band structure, the electronic band structure. This is a comparison of 2H, 4H, 6H. There is a folding of the larger degree of hexagonality means actually the folding of the bands and the appearance of more bands. This is already a spaghetti of electronic bands. We see also the indirect band gap here at about 3.4 electron volts. We have nowadays very good values of band curvatures, which are effective masses. They determine the ability of electrons to move in electrical fields, and you see the strong anisotropy as the different values of effective masses along different directions in the Jeng-Rong zone. So this and these energies between 0, the top of the valence band, and the minimum of the conduction band, this belongs to the transparent range, because no photons can be absorbed by these electronic transitions when they do not have enough energy. That means this is the upper edge of the transparent range. So how does the optical response in this range look like? I have selected a spectrum
document that is automatically generated by the EU.
I have chosen the ellipsometric spectrum on an epitaxial structure and presented it as the imaginary part of the dielectric function, of the absorptive part of the permittivity here. This is the photon energy, which is the usual quantity to show